Hello everybody to our lesson on integration by substitution. In this lesson, we're going to introduce this topic and we're going to cover one of the three most common types, and then we'll cover the other two in the next lesson. So before we can actually get into integrating by substitution, we have to learn about a new term. And that new term is called the differential, okay? So what exactly is a differential? Well, if we are thinking about what we've learned in the past, how the derivative, d by dx, of a function is the derivative, okay? We're writing that f prime is equal to df dx, right, to get the derivative. So now, if we take that, if we think of df dx more like we would think of a fraction, we can now say that the derivative of the function is the function's derivative times dx. And this is now what is known as the differential, okay? The differential is the derivative times dx. So let's calculate a couple of these. So if I have a function f of x, and this one is x squared, the differential becomes df is equal to the derivative of the function. So my function is x squared, my derivative is 2x times dx, okay? So I'm strictly looking at the function to take the derivative. What if I had a polynomial that looked like this? df is equal to the derivative of the function, so that's going to be 4x cubed. Derivative of 5 minus 5x is minus 5, all times dx, okay? So I can calculate the differential from a function by saying the differential is the derivative times dx, okay? So we're going to introduce a new letter here, u, because u is a standard we use in substitution. So I'm just really, replacing f of x here with my u. So if u is x cubed plus 1, the derivative of u, du, is that function's derivative, right, times dx. So this is the differential for this function. Now, when we start learning this, we are ready to take it to the next step, which is using this first of the three substitution formulas. And notice how familiar this is to you. The integral of some function to a power, du, is equal to 1 over n plus 1, the function n plus 1 plus c, okay? So let's note then that du is the differential of u, okay? We're not used to doing anything with this until now. So let's look at some examples of this and see how that works out, okay? So here's my equation that I want to work with. I want to integrate x squared plus 1 to the third power times 2x dx, okay? So until now, we wouldn't be able to take the integration or take the integral of this. But if I look at this from the perspective of how can I make it look something like this? Well, if I look at just what's in the parentheses as u, okay, u to the n, well, that would be u to the n. Well, what does that mean? That means I need to come up. Notice I haven't taken care of this 2x. But if I say, well, what is u? If I have a function u, I can find the differential du. I can find the differential du by taking the derivative of that function. All right, well, let's take the derivative of that. That's just going to be 2x, isn't it? So times dx. Okay, now look what I have here. I actually have the integral of u cubed, right? X squared plus 1 is u, and it was cubed, times du. Notice how du is 2x dx. I have simply substituted du for the 2x dx, okay? Now, the beauty of doing this is I have a formula here when I'm of this format. So I'm going to have 1 over 3 plus 1 times u to the 3 plus 1 plus c, or in this case, 1/4 u to the 4th plus c, correct? I mean, all I'm doing is just following my formula there. Well, now that I'm done, guess what I can do? Since I have no more operations that I can do here, I can simply substitute back in for u and say that this is 1/4 of x squared plus 1 to the 4th power plus c, okay? So this gives me a way of handling a product in this case and finding the integral of it by making some substitutions and allowing myself to just follow my formula, get the integral, and then replace or resubstitute what I had defined u as, okay? So let's look at another one, because this one worked out pretty smoothly for us, all right? Because du was already inside my integral, wasn't it? Well, what happens, and we're going to make one that's very, very similar to that, if we had the integral of x squared plus 1 cubed x dx, okay? Now, the only difference between this integral and this integral is, notice I don't have 2x, I simply have an x, okay? So I want to define, and I'll just write this one over here, u is equal to x squared plus 1, right? That didn't change. Du is still going to be the same thing. It's the derivative of this, 2x times dx. Now, I can't make this substitution anymore, can I? Because I have a 2x and an x. But what I can do is I can rewrite this as x squared plus 1 times 3. Don't I need a 2 there? So let me just stick that 2 in there, x dx. Now I have the format that I know is going to work, but I just can't arbitrarily stick a number in there because that changes the equation. Obviously, this is different than this. Unless I multiply the entire equation by the reciprocal of what I just added in there, right? Because we know when we integrate, we can just slide integers out, and sliding the 2 out times the 1/2 would give me a 1, which would make this the same problem. But I need this so that I can utilize u and du to make this work. So now I would go along and say, all right, so I'm going to have 1/2 the integral of u cubed du, right? U cubed du, well, du is 2x dx. There's 2x dx, so I can substitute it. So that's going to give me 1/2 times 1 over n plus 1 u to the n plus 1, right? Plus c, or 1/2 times 1/4 u to the 4th plus c. So now can't I substitute? And while I'm substituting, I can multiply this 1/4 and this 1/2 to get 1/8. And when I substitute in for u, it's x squared plus 1, x squared plus 1 to the 4th power plus c. So this is called multiplying inside and outside by constants, okay? And that allows me to take an equation that doesn't quite fit, like how perfectly this one fit, and turn it into something that I need in order to make work, okay? So let's see if we can't do another example here, if I can find one for us real quick, and see what we can do with one of those, all right? Let me see here. How about, let's look at the following. Let's integrate x cubed plus 1 to the 4th power x squared dx, okay? Now, I've kept my formula up here. It looks like I've got u to a power, so let's see what we can do. If I take u and make it equal to x cubed plus 1, then that says du would have to be what? 3x squared dx, okay? So let's go down here to our formula and say, all right, so I'm going to have the integral of x cubed plus 1 to the 4th power. I'm thinking this might have been my du. Okay, it's very similar, isn't it? So I'm going to put a 3 in here, and I'm going to use its reciprocal out there. And then this will be x squared, bringing the x squared down, dx. So this inside and outside, I've still got a 1, but now I can say now I've got the integral of what? U to the 4th du, don't I? Here's my du, and here is my u. So u to the n du, and then I just integrate it with my substitution formula. So I'm going to have 1/3 times 1 over 4 plus 1, u to the 4 plus 1, okay, plus c, which is going to be 1/3 times 1/5 u to the 5th plus c. And now I can substitute, and I can multiply those together. U is x cubed plus 1, x cubed plus 1 to the 5th power plus my arbitrary constant, okay? So I just wanted to introduce this most basic of substitutions, lets you get accustomed to calculating the differential so that I can make these substitutions. So on our next lesson, we're actually going to go in and cover two more formulas, one dealing with the natural number e, and the second one dealing with natural logs. So what did we learn about today? Well, we learned about integration by substitution. We learned what a differential was. We calculated differentials, and then we learned how to make substitutions with this formula in order to do the integration of some equations that we have not been able to do so far. Okay, so that concludes our lesson, and I will see you guys next time.